over today and share my screen. And today, to go over the problems, we're going to be using Python Tutor so that we can really step through each of these problems one by one. And as we're going through Python Tutor here again, you should be double checking that I have copy and pasted my programs correctly. I have the 4 tabs up here with the 4 problems preloaded. And again, the contents that I have pasted into Python Tutor right here should match exactly on your quiz the content between the 2 EOF lines, which is the actual Python code that we're going to be running. So if I think I have them all correct, but please double check that. And again, quick reminder that this is our first quiz on recursion, and this quiz is only going to be worth 4 points. This topic, though, is going to be very important for you as you're debugging your programs. A little bit this week because the programs are recursive, but again, I mostly gave you the code for this week, so maybe not. My hope is that this programming assignment this week, not too hard, but definitely in the coming weeks, we're going to be seeing some very mind-bending recursive problems. And by really studying for these quizzes, my hope is that it will make those future programming assignments much easier for you all. And again, as questions come up during the quiz, feel free to interrupt me and ask them. So the first problem right here that we have, at the very beginning, we'll step through this. We just define our function, and then we go into this try and except block. And again, the only reason for the try and except block for the purposes of the quiz is so that if there is one of these Stack Overflow errors or like that our recursion runs forever, then it's not going to run forever. It'll give us, it'll throw that runtime error, we'll catch it and print Stack Overflow. In this case, we go into 10. We'll always go into the print statement right here and then call our function. In this case, we're calling it on this list here, 1, 2, 3, 4, 5. And let's see what's going to happen. Our first problem has one of these internal or local functions inside of it. So on line 2, when we step in, we're going to create another one of these functions. Again, as soon as we hit the DEF keyword, we don't go into the function. We just create the variable with that function name. Over here, you can see here's this function object, the foo function object as well. They don't get displayed what those look like internally in Python Tutor because it's not really easy to visualize what is exactly a function. But here we have this go variable, which points to that function. So when we call go of 0 right here, it's going to execute this function. I'll press next again, and we'll go inside the function, and we'll begin with our I value equal to 0. All of these recursive functions, if they're written correctly, are going to have a base case. And in this case, the base case is checking to see whether 0 is larger than the length of the list. And in this case, it is not. The length of our list is 5. So we're not going inside the base case. We'll skip right over that, not executing line 4 right here, but skipping straight to line 5. This RET variable, common sort of name for a variable that you're going to return later. You can't call a variable return because return is what we call a keyword in Python, a reserved word, something that you can't use. So just the abbreviation ret is common to use, and we will be constructing our return value and then returning it at the end down here. Each time we go through this recursive function, we're going to be taking the position in the list over here at the index that we're currently looking at. So I is 0 right here, the position 0 is 1, and so our return value ret will start off being equal to 1 in this first recursive call that we're currently inside of. Line 6 right here is our recursive call. It is the function that we're calling inside of itself. So that's what makes this a recursive function right here. And here our I value is changing. Very important that whatever you're passing to your recursive call is going to change each time somehow that you go through it. And in this case, we're making the problem smaller by increasing the I value, that we're starting with I equals 0. We're going to be increasing the I value until we get to the end of the list. Our base case up here is checking to see if I has gone past the end of the list. So we're getting closer and closer to this base case being satisfied as we add 2, in this case, to our I value. So line 6 right here, we're going to call the go function again recursively. And as soon as I press next, you'll see down here a new frame was added to our call stack over here. Again, it's a stack because we're sort of putting things on top. We call this the top of the stack, even though Python Tutor is drawing the stack sort of upside down. This is still the top of the stack. We're always pushing our new functions, our new frames, our new set of variables. We're pushing those to the top of the stack down here. And then when we hit return, we'll be popping them off the stack. In this case, it's our second time into the go function. Our I value is now equal to 2, again, because here when we called it, we did I plus 2. And so we skipped 1, go straight from 0 to 2. Go inside the go function again and check the base case again. We're still not satisfying it, so skip over that. Create a new return value, and our return value in this case is going to be 3. And the 3 here comes from the 3 in the list. That our I value is 2, so just look up that position in the list and get 3. And go on to the next line, and we run the go function one more time recursively. Again, I plus 2, so I is going to be equal to 4. We'll scroll down a little bit over here so that we can see more. And now we're still checking our base case right here at the beginning every time. The length of our list, the index over here is 4, but the length of our list is 5. So we're still not at the base case. Still one more time through this function, return RET is 5 now because that's position 4 in the list. And then we're going to do the base case, or sorry, the recursive call one last time. This time I will be equal to 6. We will go into the base case now this time. We will go inside of here because our I value 6 is going to be greater than or equal to 5 right here. So we'll go inside and hit the return 0 right here. Again, as soon as we hit the return call, we know that we're no longer recursively calling our function. The recursive call happens here on line 6. This is after our return statement. And as soon as we hit return, we are done with this particular call to the go function. And so we are done over here. We're no longer doing any more recursive calls. We're in the base case. And so we're just going to return 0. Hit next. You can see that the return value down here is 0. And so every time we have the recursive call, we're just going to add whatever the return value was to the previous ret value. So down here in this frame right here, this return value right here will get 5 added to 0, which is just equal to 5 still. And now we have another return ret right here, return this 5. This 5 will get added to this 3 when we execute line 6 inside of this go function right here. So this return value will be 3 plus 5, which is 8, like that. One more time, we're returning our new ret value 8, and we'll press next here in a second to add this 8 up to this 1. Next, you get 9, and then that's our last time through the actual internal function here, or local function. We'll return that 9 value. That'll get returned back to this location right here inside the foo function, not inside the go function at all. And so we have 9 as what the foo function will be returning, and that is what we will finally be printing out. So if you have 9 as your answer, you get full credits. Anything else, then no credits. A lot of steps in that problem, a lot of places to get tripped up about what's going on. But any questions? Yes. Sure. So the question is, after we've already sort of pushed everything onto the stack here, and then how does the popping things off the stack, so how does it work when all the returns are going on and everything is getting added together? At this point, I've pressed the previous button to take us back into our last call of the go function. So our current line that we're going to execute next is line 2 right here with this value of I equals 6 inside of the go function. And when I do that, we'll come down here into the base case and we'll check is 6 greater than or equal to the length of our list? It is. So we finally are in the base case. And one of the key things about the base case is that when you hit the base case, that's when you're going to start popping things off of this call stack. This frames list down here, this whole thing is another name for it is the call stack. And again, the reason we use the word stack is because things only get added and taken off in one location here. It's drawn here as the bottom of the on the web page, just because as web pages grow, you add things to the bottom. So like this is what we'd consider to be the top of the web page or the top of the stack right here. Always going to be adding and removing things to whatever is on the bottom. And in this case, because we have a return call and not a recursive function, the return is going to mean that we're popping something off the stack. And the question is, what exactly are we going to do with the thing that we pop off the stack? And here, the return value is 0. For the recursive calls, the return value is usually something for the base case, the return value is usually something very simple, like 0 or 1, or an empty list, something very simple. And we are going to add that, in this case, to the return value down here. Why are we going to add that to the return value down there? Because line 6 right here, this is the line that did the recursive call. On this function right here, we were at line 6 when we called the go function with I plus 2. 4 plus 2 being 6. So this 6 here, putting us in this frame right here, was line 6 inside this function right here. So we're going to take our return value of 0, substitute it in for this function call right here, and we'll get return plus equals 0. So 5 plus equals 0, and that'll just be equal to 5 still. Every one of these pops off the stack is going to behave the same exact way, where we execute line 6 right here on the previous function down here. And so we'll take the return value that this function down here is returning, substitute that for the go function right here. That'll put a 5 right there. And so the return value is currently equal to 3. This RET right here is currently equal to 3 inside of this function right here. And so we're going to take that 3 and add this return value of 5 to it to give us an 8 right here. Press next, you see that we get the 8 right there. And we'll keep doing this over and over again, adding the return value, which is just ret, to the previous ret down here. And until we pop everything off, and then this final 9 will get substituted right here for this return and print out the 9 value at the top. So when you're working through these sorts of problems, there's always somehow like a 2 phases of what's going on. The first phase, building up this call stack with all of the different values from the recursive calls, and then deconstructing the call stack, popping everything off of it, and somehow using the return value from the bottom element to combine it with the previous frame in the call stack until you get back to the very beginning. Yes. Question is, why did we put 0 here instead of something else right here? And the answer is that for these quiz problems, well, this question is what I would call a semantic question. Anytime you're asking like, why did something happen? That's the semantics of the problem. Like, and so this is asking like, what is the problem supposed to be doing? And for these quiz problems, we're trying to think about trying to separate the why from the exactly like what or how that the problem is executing. So there's really like no why here. I just chose 0 because it's like an arbitrary number, but I could have picked any number I wanted right here, and the program would still do something. After the quiz today, we'll talk about the merge sort and the quick sort algorithms. And at that point, we'll be getting more into the why of doing something. But here, the only requirement is that this is going to somehow not immediately satisfy your base case so that it will start going into the recursive calls. So yeah, good question about the why, but these problems really focus just on the how or the what. Problem number 2. This problem, you can already see down here how we have this red error message going on, because in this problem, we have a recursive call on line 2 right here. We have this recursive call, but there is no base case anywhere. So when I start running through this problem, you can see that the XS list right here, it is in fact getting smaller. This line 2 right here is in fact getting smaller. So that was one of our requirements of recursion, is somehow that our container or whatever we're working with is getting smaller or closer to a base case. But in this case, there is no base case. There is no if statement that will prevent us from doing a recursive call right here. And so once we get to the empty list, we're not going to stop. We're going to keep on going, still going forever into empty lists. And so it's not going to stop. The way Python Tutor does its infinite recursion errors, it just tells you this red thing down here. But if we ran this in the terminal, then it would throw the actual exception and catch it and print Stack Overflow. So if you wrote down Stack Overflow, then you got the full credit on this problem. Again, the key thing about this problem here is that not only do you have to have a recursive call, but you also have to have a base case. In this case, in this problem, it's obvious there's no base case because there's no if statement. It's not always obvious that there's no base case, and you should expect on next week's quiz a problem where it looks like there might be a base case, but there is in fact never a base case that gets called. Any questions on this problem? Yes.
So Python Tutor says stack is 30. From like the actual Python perspective, what is it looking to? Is it actually just having lots of stuff to do, or
so the question is, when this runtime error indicating that you have a Stack Overflow occurs, what exactly is going on? And the answer is that Python, no matter where you're running Python from, whether it's Python Tutor or in the terminal or in VS Code or in a Jupyter notebook, no matter where you're running Python from, Python has a set stack size. You'll see that occasionally in documentation about the stack size of Python that you're running with. And as soon as your that stack is referring to this stack right here of all the functions that it currently has in memory. As soon as that passes the threshold of your stack size, then it throws this Stack Overflow error. So Python Tutor's stack size is relatively small, of 30. By default, Python, anywhere else you run it, is going to have a stack size of 1,000, so much larger. But that's also something that you can configure and change, but you're not going to need to configure it for this course. Okay, problem number 3. The key thing about problem number 3 here is that instead of having this like return variable just by itself, I called the variable ACC, short for accumulator. It's common to have your variable that you're working with to be passed in as an actual parameter to the function, and that's all that's going on right here. So again, we'll define this function, go into the try block right here, and then back into the function. We're using a smaller list now, just 1, 2, 3 as the elements of our XS list. And then define our go function. Again, the first time we hit DEF, not calling the function, just defining the function. And it's really this line right here where we actually call the function. And so we're going into the go local function right here with our I value 0 and our accumulator starting at 0. We're starting our base case over here of, again, if the length of XS less than or equal to I, and it is, so we're doing accumulator plus equals XS of I. So our accumulator right here went from 0 to 1. And now what's happening is that that 1 will be passed as the accumulator over here to the future go function right here. When we call it again recursively, press next, and you can see the accumulator down here. The new accumulator value is equal to 1 instead of being equal to 0. The I value right here got a +2, just like in our previous one. So we're skipping over this this middle element right here, and we're going to go straight to this 3 over here. Press next. We're still not going to satisfy this base case that our length is 3. That is not less than or equal to 2. And so we're not going to line 4 right here, adding to our accumulator right here. Goes from 1 right here. You can see it's 1. We're going to add this 3 element right here, position 2 of our list. It's position 2 because I is currently equal to 2. So we're going to add this 3. That'll be equivalent to 3. Add that to our accumulator value, and our accumulator value will be equal to 4. So there we get 4 right here. Press next and go back into our recursive call. And now our I value for the recursion is equal to 4. 4 will break us out of the recursion right here. It will satisfy this base case because 4 is greater than or equal to 3, which is the length of the list. And so when we execute line 3, this will evaluate to true. We'll go inside of here and do the return accumulator. When we have this accumulator pattern of passing the variable through our function like this, the return statement is going to be that accumulator. And so we'll, rather than doing return 0 here, we'll return the 4 value right here. And as soon as we hit that return 4, I'll press next right here. You can see that it's saying return 4 right here. The previous, again, we're going to pop this frame off of the call stack, and this 4 right here will get substituted for the location that we called the go function right here. So it's immediately going to get substituted right here, the 4 value, and we'll return that. So press next, and we'll immediately return the 4 value right here. Again, when we do I'll press next again, the return value right here will get substituted in for the go function right here in this previous call to the go function. And so even though accumulator right here is 1 for this function, we're not going to be looking at the accumulator value anymore like we were the ret value in the previous one. We're going to be looking at the return value down here and just instantly return that because there's no direct computation right here. It's just return whatever the return value is from the previous recursive call. So as soon as I press next, you'll see that the return value up here will not be the accumulator, but will be the return value here. I'll press next, and you can see that there's a 4 right here because that's what got substituted here. And once again, I'll press next, and the return value of the foo function will be the accumulator, and so substituting 4. In this case, problems 3 and 1 gave us different results because the lists that were input to those problems were different lists, but the functions themselves actually do the same exact thing. They just have a slightly different pattern of how they're keeping track of the results. It turns out that in Python, both this accumulator pattern and the other return pattern are equally efficient. And so you'll see people using both of these in Python. But it turns out in other programming languages, depending on the language, one of these patterns is more efficient than the other. And so in other programming languages, people tend to only use one of these patterns, where you either have the accumulator or don't have an accumulator. In Python, you'll see both of these, though. Any questions on problem number 3? Yes.
So how is the line that gets it to return 4
So there's a lot of return 4s going on here. Line 6 here is always going to be the one that's returning 4 for all of these go functions when we're inside the go function, because when you're in this accumulator pattern where it's just instantly return and then a function with no computation on this function, then the return value here will just propagate down through everything. You don't have to do any computation. So next, it's always going to be 4. So a lot of people like this accumulator pattern because it makes this final, like, going back up the call stack really easy. It's just propagate the 4 everywhere. And again, it's because on this line 6, there is no computation that happens after the go function that makes that work. Yes. Question is, does the accumulator make things slower? The answer is that in Python, no. And actually, in most other programming languages, this turns out to be faster than not having the accumulator, the other pattern. But in Python, they're equally fast. Problem number 4. So this one, what's interesting about it is that there are these 2 different recursive calls here, foo and foo. And so there's going to be a lot more to sort of keep track of mentally about what's going on. In this case, I only have a very, very small input list down here. So that's going to make keeping track of what's going on a little bit easier. But you can expect, again, in next week's version of the quiz, which is, again, worth twice as many points, for there to be some sort of similar problem, but with a larger list that will test your ability to keep track of everything more thoroughly. So I'll press next here on this foo, go inside, get inside our actual foo function right here. And we're starting off with our XS list, just having these single 2 elements inside of it, 1 and 2. We try our base case here that our length of XS equal to 0. It's not equal to 0, so we'll skip over that again. And now we're computing this return value. When we do compute this return value, line 4, simple one, no recursion going on, just set it equal to XS of 0, so the first position in this list. And now when we have line 5 right here, we have a recursive call going on. Ret plus equals foo of x, and then this slice right here. I'll press next, and the XS you'll see is now an empty list in our new frame down here in our foo call right here. And the reason for that is because XS at position 2 to the end, there is no position 2, so 2 to the end is just the empty list over here. And so we're calling this on an empty list. The key thing to keep track of when you're on this sort of multi-recursion is at this point in Python Tutor on the right-hand side over here, there is no indication about whether this function right here was called from line 5 or from line 6. Down here, this foo function, there's no way for us to know just looking at the output of Python Tutor over here, whether it was called from line 5 or from line 6. But this is something that you will need to know after this function returns and you go back to this function. You'll need to know which line to go back to. So as you're working through these things, pencil and paper, you'll need to make sure that when you're inside this function here, you know which one to go back to. Is it the first one or the second one? In this case, it's the first one because it's our very first recursive call. We're doing it with an empty list now, so we go in and we hit, backing us up to press the next button too many times. Okay. Apologize. What happened was I pressed the next button too many times. It jumped us too many steps forward. And so I've backed us up, pressed the previous button to the point where we're supposed to be. And at this point, we have only called the foo function once. We're on line 5 right here and we have not yet gotten inside the foo function. We'll do that right now. Press next. This is our first recursive call. And again, with XS being the empty list right here. Press next again. Now we're going to check this base case, and it will in fact be true. We will get a return 0 value right here. And so when we, I'll press next one last time, we have this return 0 value here. In order to know what to do with this 0 value, we have to know which line we're going back to in the recursive call over here. And again, it's line 5 because this is our first recursive call that we're inside of. Press next, and you can see that the green line here, the green arrow points to line 5 because that's the line that we just executed. The line that we're about to execute next is the red arrow, line 6. And so we're going to do another recursive call, this time with XS at 1 colon. I'll press next, and we'll go inside of the foo function again, now with this recursive call. And again, it'll be important to remember that this function right here is going, when this function returns, it's going back to line 6, not to line 5. There's no indication in Python Tutor. It does not tell you that. So you just have to make an annotation of that yourself and remember that this function right here, when it returns, it's going back to line 6 and not to line 5. I know it's going back to line 6 because you can see the green arrow here is on line 6 because that's the previous line that we executed. It's line 6 that caused the recursive call. We're now in the foo function with XS being a list with just a single element inside of it. Press next, not the base case. So we go through the recursive section of the code again. Return equals XS. There's our 2 value. and now the two recursive calls here. In this case, both of these two recursive calls, when we do the slice, it's going to give us an empty list. So we'll hit two base cases in a row. Here's the first base case. Here's the second base case now on line 6. Still an empty list, so return 0. So both of these two lines inside of this function, both line 5 and line 6 inside of this call to the function right here, returned 0 and did not modify our ret value. And so we stayed at 2. Line 5 and 6 had no effect inside of this function. And so line 4 is where we got the 2 value, and we stayed at 2. I'm going to return that 2 value now. And now we have to remember, where is that going to get substituted? Is it going to get substituted at line 5, or is it going to get substituted at line 6? And if we took our annotation correctly, we'll see that it'll get substituted at line 6. And our next line that got executed is this return ret right here. Final value after doing all those substitutions is 3, and so that'll just be what is substituted down here. So for this small list, this was just a really complicated way of adding 1 plus 2 together. 3 is the final answer. If you put down 3, full credit. Anything else, no credits. Again, for your subsequent quiz, which will be worth more points, you can expect a more complicated thing like this that's really going to test your ability to track which of these two function calls did you come from. Any questions about anything on the quiz? Yes. Problem 4 on the practice quiz. Before we go to the practice quiz, any questions on the quiz? Yes. Question is over here, why is this right here not an error? And we're gonna go back to Python here for a second. We'll run Python interactively. Again, anytime you're trying to just like, you have a question about Python that you want to understand, interactive Python is the best way to do that. And you get into interactive Python just by typing Python 3 in the terminal. Let's start with a simple list similar to the list that we had in the problem like this. And if we have XS at 0, that gives us the expected 1. XS at 1 gives us the expected 2. And the question is here, if we do XS at 2, we get this index error value. This right here is called the subscript operation, or the get item operation, or the square brackets, or the index operation. This is not what we're doing in the quiz, though. In the quiz, there was also a colon after it. And here, when you have a slice operation, you know it's a slice because it has a colon. A slice operation will never give you an index error. It's just if your slice does not return anything, it gives you the empty list like this. So it's a subtle Python technicality, but one that is, you'll definitely have to, it's going to come up throughout the course, the difference between the slice and the index and their sort of failure modes down here. This is one of the things that some people dislike about Python, that the slice and the index behave differently. One throws an error, one does not throw an error, but it seems like they should behave the same because the syntax is so similar to each other. But it turns out that this just has, having it go to an empty list makes certain algorithms simpler to write. And so our benevolent dictator for life, Guido von Rossum, has decided that this is how the slice should behave, and this is how the index should behave. And everybody who uses Python just has to deal with it. Good question. We have, let's see, so there was a question about the problem 4 on the practice quiz. I don't want to go to that just so that we have time to cover everything that we need to cover today, but I'll be happy to answer that after class or in the lab or office hours, any other time. Go ahead and total up your points. Again, it's out of 4, each problem worth 1 point, and pass the quizzes up to me. Any other questions that I don't have yet? We're going to be going over the merge and quick sorts notes next here. So getting out your the handout with that would be good. That handout looks like this one here. We're going to be going over this next, what you'll need for the homework assignment today or this week. So go ahead and pull that out. As you're pulling that out, some more quick announcements. I put them right here. So just a quick reminder from last class, we covered two methods of getting the runtime from a recursive relation, the iterative substitution and the master theorem. I guess I regret talking about the iterative substitution at all because a number of people have mentioned being confused about that. I guess the main motivation of that was just that that it's not important. There is this other technique. You'll see people talk about this other technique, but master theorem is the thing that we'll use for this class, this point forward. So that's the thing to actually understand. In non-data structures courses, but in courses like discrete math or maybe upper division CS courses, the way that you would prove the master theorem is by using this iterative substitution technique. But we're not covering that. We're just talking about how do you use the master theorem. And so understanding this is the important thing. And again, if you still feel like you have questions about the master theorem, we will probably get to more examples of that today. But in the lab this week, you'll have lots of opportunity to practice and review that. One last quick announcement administratively is we're about 1 week ahead of schedule right now. So we've been going very fast through the course, especially through this like recursion, searching, sorting section of the course. The motivation for that is, again, I have at the end of the semester, probably baby will be coming and we'll be taking 2 weeks off for that. Normally I leave at the end of the course, just like a 1 week gap time. So we're at this point on schedule to go at a normal pace on all of the other topics and cover all the material. So yeah, if you felt like the last few topics were extra hard or like you needed more time for those things, that's because normally there is more time for those things. But you should also feel good about yourself for being ahead of schedule right now. Today in class, we're going to talk about your upcoming homework assignment about sorting. And again, I've given you the not just pseudocode, but legitimate code for two important sorting algorithms, this merge sort algorithm and this quick sort algorithm. Out of all the sorting algorithms, these are the most fundamental of the two. And these are the two that if like in an interview situation, for example, people were to ask about sorting algorithms, these are the only two that they would ask about. High-level overview of sorting. There are many sorting algorithms that are traditionally covered inside of a computer science class. Again, we're not going into detail on all of these, both because we're going a little bit fast through this section, but also because this class is really more geared towards the data science major rather than the computer science major. So these top sorts up here, these really bad sorts, we're just not going to cover at all. They're really bad because their worst case runtime is n squared. We're not going to talk in detail about the differences between each of these columns. We've talked a little bit about the best case runtime versus the worst case runtime before. In general, people don't care too much about the best case runtime of algorithms. They care only about the worst case runtime or this like average typical case runtime. In a data structures class, it's typical to mention that the fact that there is this average case runtime, but actually talking about how you compute an average case runtime is extremely difficult, requires that you have an advanced understanding of probability and distributions. And so this is something that's normally saved for like graduate level computer science courses to go into detail on average case runtime analysis. So we're, again, focusing on this worst case runtime analysis, but people do talk about these other columns and you'll see them. And it's good to have some just rough intuition for them. We'll talk, the main way the average case runtime will be important to us is when we cover this quicksort algorithm here in a little bit. We'll see that the average case is different than the worst case. And in practice, merge sort has the best worst case runtime in login, but quicksort is usually faster in practice. And even though it has a worst case runtime, it has the same average case runtime. And so it's usually faster in practice. Not this week's lab, but next week's lab, we'll do more just like experiments of these different sorting algorithms and actually measuring their runtime and comparing to this table. So the important thing about this table right now is just that merge sort is going to be our best sorting algorithm, and it will have an in-log-in runtime. In Python, in every programming language, there is a sorting algorithm that is built into the programming language. And in Python, the built-in sorting algorithm is called timsort. It is named after a famous Python programmer named Tim, who invented it just for the Python programming language. And you can see that the worst case and average case behavior asymptotically is the same as merge sort. But it has some like extra conditions that help it work in best case scenarios to be linear time. And so in practice, this is a really, really fast sorting algorithm. And after Python adopted timsort, most other programming languages are now moving over to this timsort algorithm. There is a theorem inside of computer science. We're not going to cover this in detail, but it says that every comparison-based sorting algorithm, so every sorting algorithm that works like in general for every possible thing that can be sorted, has a worst case runtime that is no better than in log n. Again, you should think of the omega over here as like a lower bound. You cannot do better than in log n. So the worst case runtime of every sorting algorithm is omega of n log n. And that tells us that, in fact, merge sort, because it matches that n log n bound, is the best possible sorting algorithm that we can do. And so that's why we'll be spending a lot of time on it, and your homework is about merge sorts. Super fast, high level overview of all of this stuff. If people have questions about this, happy to talk about it offline or during the lab time. We're going to switch over here to our terminal session and start talking about the merge sort and quicksort algorithms in detail. And I'm also going to do a little bit more live programming today than we've done in class. I think one of the most useful things that you can do as a junior sort of programmer, developing programmer, is seeing more experienced programmers code, seeing how they tackle various problems, so that when you run into those problems, you can just shortcut to the good solutions rather than having to find all of the bad solutions yourself and slow down that way. So we're going to spend most of the class time today in the terminal here. And again, I'm going to do a lot of fancy terminal things, a lot of fancy Vim things, a lot of fancy PyTest things. There's no expectation that everybody takes away 100% of this. I would be shocked if any person is able to take away 100% of what we're going to cover right now. But really what you should be focusing on is finding what were the pain points when you were doing your previous assignments, and thinking about how am I avoiding those pain points in this assignment here, so that when you're working on your future assignments, you don't have those same pain points. And again, one of the reasons why this, well, there's two reasons why this, the homework this week is a little bit easier than the previous ones. One is I try to time the easier homeworks for like midterm season when other classes are more difficult. But also I really want you this week to be focusing on your like the things that are not graded in this class, like just getting a good workflow set up and being efficient in the things that you're doing. So because the programming is a little bit easier, you'll be able to focus more on these maybe more ethereal, abstract concepts. So the first thing you'll notice is you can't see my desktop anywhere. I have used my entire screen real estate. Real estate is our most valuable resource, and so you want to use it all. I only have a 12-inch screen on my laptop, but somehow I am able to see more things than most of you all are able to see on like your 15-inch laptop screens, because I'm actually using all of the pixels on my monitor to display interesting things that will help me solve the problem. I have two terminal windows open here, and again, I didn't do anything like fancy to do this. I just literally opened two terminals and connected both of them to the Lambda server. And I'm gonna move both of them into my project folder where I will download the project. Again, these two terminal windows, they're totally separate from each other. So their working directories are separate from each other. If I want to change the working directory, I have to do it in both locations, not just a single location. And I have a bunch of things already downloaded here, including this sorting problem. I'm gonna go ahead and delete that for a second, rm-rf sorting. And it would be git clone https:// github.com/mikeisbicky/sorting and so on. We'll get you the assignment and ls, there it is again, cd into that, and ls, there's all of our problems. Again, down here on the bottom terminal, I am in my sorting folder. In the top terminal, I am not, so I should cd into that folder like this. And now they're both in the same location. Again, once I feel like now I'm sort of set up, my two terminal sessions are ready to go. And so I like to just reset both my sessions, clear off my workspace so that everything I do now is just dedicated to the actual coding that I'm about to begin doing. Are there any questions at this point about the setup of where we're at, Jonathan?
Oh,
So I use what's called a windowing desktop, which automatically arranges my screen for me. So I have hotkeys that move my windows around for me. I'm not using the mouse at all here. Just basically like Vim for Windows. And you don't have to do something like that, but you should spend like the 30 seconds formatting things, moving things as makes it comfortable for you to work. Yeah. Was there a question? No other questions? Yes.
I'm so sorry, where are we again?
So I'm in my sorting homework assignment, which I just cloned from GitHub. Press down here, Control R to git clone. This is the command that I ran to get the homework assignment, and we are now inside that folder. Question is, do you have to fork this assignment to run this git clone command? The answer is git clone will work whether you fork it or not, but for your homework assignment, like all the homework assignments, you'll have to fork it and then upload all your changes to your fork. So you're welcome to clone mine initially and then start working, but then at some point on the GitHub interface, yes, you'll have to fork. Okay, so the first thing I'm going to do is just take a look at this sorting.py file again in Vim, sorting.py like this. And then down here, it's always good practice to run all of our test cases just to see what's going on. So it's Python 3-m pytest. And you see that there's two test cases down here that we're looking at. So if I type ls tests like this, we have these two test case files. And the first thing that you'll see is we're getting this module not found error, no module named hypothesis. We're introducing a new testing library this week called Hypothesis, which is extremely powerful. In order, anytime you see this module not found error in Python, there's usually a very simple solution to that of pip3 install, then whatever the name of the module that was not found was. So in this case, it's hypothesis. Pip3 install hypothesis will install that for me. And now when I run my PyTest, I'll still get error messages because it's all broken. I haven't done anything yet, but it's actually running the PyTests. So what we need to do next is we need to look at those test cases and try to figure out exactly what's going on in this hypothesis library and what makes it special. Why is it good? Up here in the top-hand window, well, actually, before I do the correct thing, I'm going to do the thing that I've seen the vast majority of you doing, and I want you to break this habit this week. So I don't want to see after this week, I don't want to see anybody doing what I'm about to do. The bad thing that I'm about to do is I'm going to use the CD command. I'm going to CD into this test folder like this, and then I'm going to use Vim to open up one of these files, test_main.py like this. I broke up my command of opening up my test cases into two separate commands, seeding into the tests, and then Vimming, opening that up. That's not a good practice to do for many reasons. One of them is, okay, so I am able to open this file now, but now I can't run my code. If I try to do something like Python 3 of this sorting.py file, it's not going to work because I no longer have the sorting.py file in my working directory. My working directory has changed to this tests folder, and my sorting.py file is in this folder down here. So in general, once a developer has moved their terminal session into what we call the root of the project that you're working in, the location where you get cloned, we never want to touch the CD command again. Instead, we want to use relative paths to reference all of the files that we're working with. So down here, instead of doing CD tests and then Vim, I will do Vim tests/test_main.py like this, opening the file in just a single command. And now I can open it in just a single command. And when I quit out of here, I'm back into my standard working directory, can directly access the sorting.py file. This will let me use many advantages of this. Another advantage is it lets me use the up and down arrows to get back to commands, and they're always going to work because they're all based on the same working directory and not based off of different working directories. We'll reset down here to clear off all of that information again. And the next thing that I'm going to do is say that, okay, I could open in this second terminal window, I could open a second Vim session like this and have two separate files open in two separate terminal windows, but then I don't have a terminal window to actually run commands in. And the whole point of me having two different terminal windows here is so that I can look at the code in one window and run commands in the other window. When I run the commands, I'll be looking at the error messages. So something like Python 3-m PyTest down here. I'm going to be looking at error messages down here, and I want to be able to see both the error messages and my code at the same time. If I have to be doing like switching back and forth to see both of those things at the same time, then that is very unproductive, and I don't want to do that. So I always have one window, one terminal dedicated just to running commands, and the other window dedicated to looking at code. That begs the question, how can I look at multiple files at the same time in Vim? I think I might have done this in class before, but it's :tab E will open up another tab inside of Vim. And in this case, the file that I want to go to is again inside of this test folder. So it'll be tab E test:_main.py like this, again specifying the relative path right here so that I can open it from the same location that I have my sorting.py file opened up. I have two files opened up now, this sorting.py and this test_main.py, and I can press GT to go back and forth between these two tabs. Again, one of the things that you should be focusing on during your assignment this week is getting more efficient at your Vim movements. And again, hopefully the code will be relatively easy, and that will let you focus on working with the editors in your environment better, so that when the code starts getting really hard, you'll have good tools at your disposal in order to be able to figure out why the code is not doing what you want it to do. Okay, so now I'm in my test_main.py, and I want to look at some of these test cases down here. And so we can scroll down like this, and here is the first test case right here. You'll notice that this is a little bit different because on line 12, there's this thing @given right here. This is the thing that is special about the hypothesis library, is it introduces this @given command. And what this does is it means that this test case is not a test case on one particular set of values, but the PyTest library is actually going to try thousands and thousands of possible lists on this test case, and it's going to work, your code will have to work with all of them. This is called property-based testing because this right here specifies a property that our functions must satisfy. In this case, what this property is testing, so line 14, 15, 16, it's creating 3 variables right here, string 1 sorted, string 2 sorted, string 1, 2 sorted, based on these inputs right here. These inputs are lists of integers, and string 1, 2 is just a sorted version of the concatenation of string 1 and string 2. And so this is testing that our merged function right here must be string 1 sorted, that if you pass in 2 sorted lists like this, a sorted list on the left and a sorted list on the right, then the output will be a sorted list, which will be equal to just first concatenating and then sorting. This merged function is the only function that you really have to implement from as part of this homework. And my hope is that it will be relatively easy for you to implement. At this point, though, in order to be able to talk about merge sort, I'm going to need this merged function in order to do it. Really quickly, so I'm going to go over here. So I press GT to switch my tabs right here. I'm going to press slash. Again, slash is search. I'm going to go underscore merged, find this function. I'm going to use the curly brace to jump down here to the implementation of this function. I'm going to copy and paste from my solution into here, into the implementation. So if you're like super fast typer, you could type the solution as we go through it. But my recommendation here is that you not do that and try to work on it on your own. So and Vim sorting this. When I so up here in this top terminal window, I have the solution open slash underscore merged again to just find that location. Here's the actual implementation of the code. And now we'll just really quickly see what is a tool that I use for copying and pasting code. Well, if I try to just use my mouse to like copy and paste between these things, it's not going to work because there's these numbers in the way over here, and it'll be copying and pasting those numbers. So I'll do :set no number to remove those numbers, and then I'll zoom out just a little bit so I can see it all at once and copy and paste, copy that down here in Vim, paste that, fix any indentation issues, save that up here, :QA, exit, and now we have a really quickly implemented solution to the merged function. I want to check to see if that actually works down here. And so in order to do that, you'll notice that previously I had 10 failing before I implemented that and 2 passing. Let's see what's going to happen when I rerun this PyTest. And you can see that there are now more passing tests down here, and there are no tests here that list that merged function. I want to really be double check though that these tests that are passing are all the possible tests about the underscore merged function. And so what I want to do is I want to figure out how is there a way that I can only test the merged function and not all of these other functions all at once. I know how to do that only because I looked it up this morning on Google. The thing that I looked up on Google was in PyTest only run some tests like this. The first result right here going to Stack Overflow, always a good place to look for these programming problems. And the first answer down here mentions there's this -k option. And that if you do -k and put a string to the right of it, it'll only run tests that have whatever matches your pattern over here. And so I'll just add -k over here and add underscore merge to only run the tests related to the merged function. And here we can see that we're now passing all of the tests related to the merged function. In general, one of the things that at this point in your like programming careers you want to be getting into the habit of is that if there is something that you think like you should be able to do, like somebody has probably wanted to only run some test cases at some point, then that thing is going to have been implemented. And just a quick Google search will tell you how to do that. And then you have this new tool to add to your toolbox to make sure that you can focus in on only some tests at a time. So that was the dash K and then underscore merged over here. The reason I put underscore merged again is because that matches these test cases right here. Okay, so now I'm ready to go on to the actual merge sort function itself. If I keep scrolling down a little bit, then I get the merge sorted function. Again, in Python, it is traditional that you make your functions that do not modify containers, but return copies of containers. You make those past tense functions, merge sorted. This returns a copy that has been sorted. It has this merge here out in front just to indicate that it's using merge sort to do so. And now I'll go through and implement this and explain how exactly the merge sort function works, the merge sort algorithm works as we do so. And we'll see how to effectively use the PyTest library to check our work as we're going on. The first thing I'm going to do is I'm going to change my PyTest command down here so that instead of running the merged test cases, it's going to run the merge sort test cases like this and hit enter. We can see that there's 4 different test cases, and looks like 3 of them failing, but 1 of them is already passing. The idea of merge sort is I have some pseudocode up here. I also, again, over here gave you the actual code that's going to work. The idea is well, let's back up. Before talking about the idea of exactly what merge sorted here is going to do, I want to revisit this idea of thinking about the why of a recursive algorithm. That again, the quiz is focusing on the how and the what, and now the homework's with a real algorithm thinking about the why. The first thing that I always do whenever I think I might need a recursive algorithm is I always start with the base case. And in this case, for anytime we have a sorted list, the idea is that if the list only has 1 element, then it's already sorted. So like the simplest somehow possible list is a list that only contains 1 thing. And the base case is always going to somehow be the simplest possible thing. So if our list already has 1 element, it's already sorted, so we'll return just that list. So if the length of XS equals 1, then we'll just return the list itself like this. So we haven't fully implemented everything. All we've done is we have this like 1 case that we know is going to work, and it will be correct basically just by definition. I'm going to come down here and see how this new code that I've ran has affected my test cases down here. And so I'll press the up arrow and rerun this. And you'll see that all the test cases are still failing. Again, I want to zoom in on just 1 test case at a time. So I'm going to add another flag down here to my PyTest, this dash X. We've seen it before, zooming in on just the very first test that fails and this test merge sorted. And we're going to take a look at this output from PyTest with this hypothesis library and see what's going on here. The important thing here in this output is that right down here under hypothesis is the examples of the strings that it's giving you, or the thing that it's passing in to the algorithm that's causing it to fail. So here under test merge sorted, the first parameter that we're passing in is an empty list. And so we're failing here when our merge sorted, when this thing over here is an empty list. And so in order to fix that, we need to change this so that it works on an empty list. And an empty list is another great sort of base case scenario that my pseudocode up here only talking about if it has 1 element, but really if something has 0 elements, then it's also already sorted. So I'm going to add that into my base case. If length of XS equals 0, then also return just that list itself. I think in the pseudocode, or in the real code that I provide you, these 2 things are combined into just a single line. So let's save that up here. Again, my workflow that I always do is I do :W up here when I save something, and then down here, press the up arrow to rerun that test and evaluate how the output has changed. come up here, and now you can see that down here, this falsifying example of this merge sorted function has changed. String 1 now has this more interesting list inside of it. It has 2 things inside of it. So we now, outside of the base cases, outside of the most simple situation, and have to think about how to deal with the situation where we have 2 separate things. The idea of the merge sort function is that we're going to break the list in half. So we'll have left, I think first created this variable mid equals the length of XS divided by 2. So this is somehow like the middle of the list. Left equals a slice of our list. The leftmost portions, right equals the rightmost portions. And the idea here is that if I already had a function, that the key thing to think about when doing recursive functions is that if I already had a working sorting function, then I would know that I could just use that to sort the thing on the left and use it to sort the thing on the right. Use my working sorting function to sort the subproblems over here, the left side and the right side separately. And so I'm going to do that. I'm going to assume that I have a working sorting function of merged sort left, and I guess it's merge sorted is the name of the function, and then right equals merge sorted right. If I already had a working sorting function, then this thing would work, and now the left and the right would be sorted over here. The left and the right would be sorted. And I know how to combine 2 lists that are already sorted because we did that up here in our underscore merged function. So I know how to combine these 2 things together. And something like return underscore merged of left and right. And I'll go ahead and run this, save that up here, come down here, up arrow, rerun that. And you can see that that has caused it to pass some additional test cases. It now has 2 passed instead of 1. And actually, this is the fully correct, fully working merge sort function. And the idea is just that, again, that we've somehow identified smaller subproblems right here. And we assume that if we were able to magically have those things sorted somehow, if we were to have them sorted somehow, then we could, we know already how to combine them with this underscore merged function, and then everything will just work. One last thing to talk about today that I want to make sure that we do. This is the implementation that we have right here. It matches what's in your notes, and it is fully correct. The only thing that is different, that making it not pass the test cases, is this CMP function up here. CMP allows you to change the way things are ordered using these functions up here. And for your homework assignment, you'll have to use the CMP function in order to or you'll have to modify your code down here to use the CMP function instead of just a direct comparison. We'll stop here for today. We'll do a little bit of lecture stuff on Lab and Friday to review some of this and maybe take it at a slower pace. But at this point, you know everything that you need to complete your homework assignment should you choose to do that. So we'll stop today. Oh, I went a minute over. I apologize for that.